Hi everyone, welcome back to Mind Maths with Amina. I'm going to continue solving questions given in the Statistics 1 study guide given by University of London for their EMFSS program. Okay, the chapter is chapter 3 called Probability Theory, and this is the fourth practice question. Okay, they're asking us to use a diagram or otherwise to prove the following. Okay, so the first thing that they want us to prove is that the probability of A plus the complement of A has to add up to a 1. So the first thing that we should recognize is that by definition, an event A and its complement are mutually exclusive, so there's no overlap, and they are collectively exhaustive. In order for you to get a better understanding of what these two terms mean, I'll draw a Venn diagram. So suppose we have a set S and there is an event A and an event the complement of A. Okay, so as you can see, if I shade these two regions, so if the event A has all of these elements in it, then the event in all the events elements in the event A complement have no overlap with A, and combined they give us the whole sample space. So what this means is two things: that the intersection between A and its complement is empty, and the reason being is that these two events are disjoint, that is, they are mutually exclusive, and their union is the whole sample space, which shows that they are in fact collectively exhaustive. Okay, so what does this mean for our question? If I want to find the probability of A union A complement, I know it's going to be the probability of A plus the probability of A complement minus the probability of A intersection A complement. Okay, so the probability of A is just probability of A depending on the elements in it, and this is the probability of A complement. And since there is nothing inside the intersection, the set is empty, so the probability of an empty set happening is 0, whereas the probability of the whole sample space occurring is 1. So therefore we have shown that the probability of A complement is equals to 1 minus probability of A. So we've solved part A. The second one is that the probability of A union B is equals to probability of A plus probability of B minus the intersection of both. Okay, so they want us to use a Venn diagram. So let's make two events, set A and set B, and we can say that elements in A which are not in B is A, B comes in the intersection, and C element is in B and not in A. Okay, so what is the probability of A union B? Union is both of them, right? So either A or B, it could be in any. Okay, so it's going to be from the shaded region, we can say it's A plus B plus C. So if I do a little bit of manipulation, if I write A plus B plus C plus a B, then I've actually added another B which wasn't here, right? I just need an A, B and C. So this is an additional element that I've added. So I need to subtract it because both of these expressions need to be same. Okay, so A and B is actually a probability of A, C plus B is probability of B, and B is the probability of A intersection B. So we've proved part B. Okay, moving on to part C. If A implies B, then probability of A is less than probability of B. So the question is, if A implies B, then probability of A is less than probability of B. What does this expression mean? First, let's talk about that. If it's saying A implies B, it's the same as saying that A is a subset of B. So that if there's an element X in the set A, then it has to also be in the set B. I'll just write this down. Hence, all elements in set A belong to set B as well. Okay, so if let's give ourselves a nice visualization of this concept as well. This is the sample space. Let's just say this is, and A is a subset of B. So this is A, this is B. This white, this yellow circle set represents all elements in set A. Okay, so as you can see, if A is a subset of B, then the intersection of A and B is simply A itself. So whenever I write the probability of A intersection B, I know that the intersection, even if you don't have a subset, the intersection is always a subset of both. For instance, you can see B, so the intersection in this case is a subset of set A. The intersection of these two is a subset of the set B. So this is just a fact. If I use this fact here, then what I can tell is that the probability of A intersection B is definitely going to be less than the probability of B because it's a subset. However, we also know that when we have a subset, when A is a subset of B, then A intersection B is A itself. So the probability of A intersection B is probability of A. This only happens when you have a subset. Otherwise, this is not true. Okay. For instance, you can see in this case that A intersection B is not equals to A, and A intersection B is not equals to B. So this only holds when one is a subset of the other. Okay. So when I substitute this expression over here, I'll get a probability of A being less than probability of B, and that is exactly what we were supposed to show. So we've done part C as well. Let's do part D. Now we have 3 events and they want us to prove the formula for the union. Okay, this might be a little bit messy. Okay, part D. Again, we'll have to do some kind of manipulation like I did over here. So there was a manipulation over here. We'll have to do something like this again. Let's make a big Venn diagram. And we have 3 events, A, B, C, A, B, C, and let's label them A, B, C, D, E, F, G. Okay, so the union is A or B or C. So it's either one of them. Okay, so I can see the probability of A union B union C is A plus D plus G plus E plus B plus F plus a C. And the hint given in the question is that I need to write probability of A, probability of B, probability of C. So let's write this out first. So the probability of A is actually an A plus a D plus a G plus an E. That's A. And what about B? We have a B plus a D plus a G plus an F. Okay, but we actually used up these 4 here, and now we've used this one here and this one there. So that means I've added these extra. So if they're extra, that means I need to actually deduct the things that I'm adding extra. I added an extra D and I added an extra G, so I should actually deduct them because I added extra. Okay, probability of C is C plus a E plus a G plus an F. Okay, so we were allowed to use a C, so that's here. But now I've added extras E, G and F, which I had already used up, right? So they're extra terms. So if I've added something, I'll have to deduct it. So I'll have to deduct a E and a G and an F. Okay? Okay. So the first 3 expressions I have now. Probability of A plus the probability of B plus the probability of C. So these 3, this is the probability of A, probability of B, probability of C. And now we have this expression of minus DG DGEGF. Okay. Now it said that the next expression I should have, and it should be an B, A intersection B, A intersection C, and B intersection C. Okay, let's find this out. So the next expression they expect me to have is an A intersection C. Okay, and A intersection C is actually E plus G. And A intersection B is a D plus G. And a B intersection C is a G plus F. So let's see if I've properly used these. I was allowed an E, I did a E. I was allowed a G, I did a G. I was allowed another G, I used it. I was allowed a D, I used it. I was allowed an F, I used it. Oops, but I've used an extra G. Okay, I wasn't allowed to use this because I need to make sure these two expressions are the same. So if I've deducted a g which is extra, in order for both the expressions to be the same, I'll have to add it. Okay, so what does this become? E minus g is the probability of A intersection C. D and G is the A intersection B. G plus F is a B intersection C. And G is actually where all three of them overlap. So this is the overlap between all three sets. So it's the intersection between A, B, and C. And therefore we've proved part C. This is what they wanted us to prove. Okay, we've done one question. Let's move on to the next one. It says in a class of 35 students, so that means the cardinality of the sample space is, cardinality means the number of elements in a set, okay? So there are 35 students in the sample space, 20 have taken economics, so economics is taken by 20 students, history is taken by 15, and politics is taken by 10 students. Okay, of these 9 have taken both. Okay, so history and economics and history, 9 total people have taken. Okay, 9. Okay, then 5 have taken both economics and politics. Okay, economics and politics is taken by 5 people, and 6 have taken history and politics. 6. Okay, and 3 have taken all 3. Okay, so the intersection between E and P and H is 3. So let's draw this. Let's make this sample, which is 35 students. We have economics, we have history, and we have politics. Okay, it said that there are 3 students who have taken all of them. Okay, so 3 is the intersection between all of them. The intersection between history and politics is 6. So we've already written a 3 here, so that means there should be another 3 here. Okay, the intersection between economics and history is 9. So if 3 are over here, then 9 minus 3, okay, 6. 6 should be here. Oops, 6. Economics and politics. Okay, 5 total students have taken economics and politics. So this region should have 5 people in it, because 3 we've already listed. That means we have 2 here. Okay, in total there are 20 economics students. So a 6 plus a 3 plus a 2 plus a number should give me 20. So 6, 7, 8, 9, 10, 11, this is 11, and then 20 minus 11 is basically a 9. So we have 9 students who are taking only economics. Okay, next, history. 15 students take history. So 6 plus 3 plus h, 3 plus h is going to give me a 15. 6, 7, 8, 9, 10, 11, 12. Okay, 12 plus h. So 3 students take history only. Okay, now politics, we need to make sure that all the elements over here add up to a 10. So 3, 4, 5, 6, 7, 8, 9, 10. So there should be 2 over here. So what is the union? What are the number of elements in E and either E or H or P. So it is a 9 plus a 6 plus a 3 plus a 2, all the ones taken English, and then a 3 plus 3 plus 2. Okay. 3 plus 3 plus 2. Let me recheck. 9, 6, 3, 3, 3, and 2, 2. Yeah. So total 28 students take either history or so 28 students take either English or history or politics or all, or maybe just two of them as well. What I can do is that I can shade this region as the union. However, the total students in the whole school was in the sample space was the 35. So there are students who actually haven't taken either of these three. So since there were a total of 35 students in the class, so a 35 minus a 28 is a 7. So there are 7 students who are outside. Okay, the question was, what is the probability that a student chosen at random from the class has taken at least one of these subjects? Okay, so the probability that at least one subject is taken means that we need to see the probability of E, English, union, H, union P. So either English or, remember, union is associated with the word or, intersection is associated with the word and or is associated with the plus sign, and is multiplication. Okay. So in order to find the probability, we need to see the number of elements in the favorable set and total number of possible outcomes. So the favorable outcomes are 28 and total outcomes are 35. So that's basically the probability. Okay, next question. Two fair dice are thrown. Okay, two fair dice. Dice number 1, dice number 2. I always like giving myself visualization. Possible outcomes are 1, 2, 3. No, dice. Oh, sorry. Not a. Yeah, dice does have 6 options, right? 1, 2, 3, 4, 5, 6. A coin has head or tail. Okay, so this is a dice. 1, 2, 3, 4, 5, 6. What is the probability of 2 6s occurring? Okay. There again, like I solved such a question in 2 ways, remember. One, we can do the counting principle. Let's revise that. Let's do the counting principle first. So the counting principle helps us count possible scenarios. Okay, so for us to count the total number, maybe nobody knows this sign, total number of possible outcomes is the first dice has how many possible outcomes? 6. So there are 6 possible outcomes that the first dice can give us, and there are 6 possible options for the second one. So there are 36 possibilities in total. But what is the probability of 2 6s? Okay, this means that the first die must show a 6 and the second die must show a 6. Therefore, there's only one option here. There's only one possibility here. For instance, in this case, there are 6 possibilities here. There are 6 choices here, right? So the total number of favorable outcomes is that the first dice can only take a 6, so only one option. So 1 into 1 is a 1. Hence the probability of 2 6s is number of favorable outcomes over number of possible outcomes. So this is you using the counting principle. But there's another way to do this, that what you can do is you can define a random variable x, and you can call it that the upturned face of die is a 6. Okay, so they want what is the probability of getting 2 6s, right? So basically they're asking you that both the number of upturned faces both of them should be a 6. Okay, so the first getting a 6 is, now I'm just looking at this dice, it will get total number of possibilities is 6. So, and a 6 occurring, the chances of us getting a 6 is a 1 by 6. And what about the second die? In the second die, a 6 occurring, if the total number is 6, 1, 2, 3, 4, 5, 6, and 6 occurs only once. So there's a 1 by 6 chance of a 6 coming up on the second one as well. So total probability is going to be a 1 by 36. So you'll get the same answer using both methods. Okay, part B. What is the probability of at least 1 6? So for instance, it says that at least 1 6. That means this could be a 6 and this could actually not be a 6, right? Or this could be not a 6 and the next one is a 6, because it requires us to have at least 1 6. What's the next option? There could be more, right? So that means that this could be a 6, this could be a 6. So according to the counting principle, if there's just one option here and not 6 means the remaining, what are the remaining options left here? 1, 2, 3, 4, 5. So the first die has to show a 6, so there's just one possibility here and there are 5 possibilities here. So a 1 into a 5 will give us a 5. Okay, not a 6. 5 options here and 1 option here, right? So 1 into a 5 is a 5. Then just 1 option here and 1 option here. So 1 into a 1 is a 1. So what are the total favorable outcomes? We can see that there are a 5 plus a 5 plus a 1, 11. Hence, the probability of at least 1 6 is 11 by 36 according to the counting principle. Okay, and therefore we could have actually solved it by defining the variable as well. So this is, let me just make an arrow. This is the first way of doing it and this is the second way of doing it. So over here I have done the counting principle, and let's do part B using the defined variable x. Okay, so okay, what I'm interested in, that I need to find the probability that the number of upturned faces that are 6 is at least greater than 1. So we need either we have one upturned face which is a 6, or we have both of the dice showing a upturned face which is a 6. An easier way of actually solving this would be if I do this. X is greater than equals to 1. So since probabilities add up to a 1, so this should be strictly less than 1, probability of x less than 1. There's only one option that you get no 6, right? So the only way you don't get a 6 is the first coin doesn't show a 6. There's a 5 by 6 chance of that happening, and the second one also doesn't show a 6. So we have a 1 minus 25 over a 36, and therefore that gives us an 11 divided by 36. However, we can also actually solve it by finding out this. Okay, so if we want one upturned face to be a 6, it could, like, the first could be a 6 and the second is not a 6. So this is one possible way this can happen, or it could be that the first is not a 6 and the second one is a 6. And when it comes to the probability of both being 6s, we've already calculated that in the first part, which was a 1 by 36. So this was just a 1 over a 36. So overall, our answer will be 5 over a 36 plus a 5 over a 36 plus a 1 over a 36. So we get an 11 over a 36. What I would personally recommend is, obviously you do your own thing. You pick the method whatever is intuitively appealing to your brain. But I'm just letting you guys know that this is the method that I have used whenever I've solved such questions. So this is my personal preference. This is just my personal preference. However, preference. However, obviously, you're free to choose whichever method you like. They all give us the same answer. Okay, next question. And I think, yeah, we should do 2 more and then end this lesson. Okay, a student has an important job interview in the morning. To ensure he wakes up in time, he sets 2 alarm clocks, how efficient, which rings with probabilities 0.7 and 0.9. Okay, so the first clock ringing successfully is 97%, and the second one ringing is 99%. What is the probability that at least one of the alarm clocks will wake him up? Okay, so they want us to find the probability that at least one of the clocks rings. Okay. So again, if I use my technique, I would just do 1 minus the probability that none of them ring. So the probability of that happening is since the probability of the first ringing is a 0.97, so 1 minus a 0.97 is a 0.03, and a 1 minus a 0.99 is a 0.01. So this will give us answer 0.9997. Another way that you can do this as well is that you can just see all possible scenarios and may ensure that at least one of them rings. So for instance, it could be possible that the first one rang but the second one didn't ring, or it could be that the first one didn't ring but the second one did ring, or it could be that both of them rung. So this is going to give you the actual answer. This was pretty short and easy. This eighth question is easy as well. A fair coin is tossed 10 times. This was a trick question. It's a fair coin. What is the probability that the 10th toss results in a head? Is simply half because the coin is fair. If the first 9 tosses gave a 4 heads and the 5 tails, what is the probability of the 9 toss being head? Again, it's a half because all of these tosses are independent of each other, okay? The fair, if you have a fair coin, it's not biased, then the probability of head occurring is a half on each throw, and the probability of tail occurring on each throw is a half. So the answer to all of these questions is just a half. The last question for today, before I wrap up this lesson, is as follows. The successful operation of 3 separate switches is needed to control a machine. Okay, there are 3 separate switches. If the probability of failure of each switch is 0.1, okay, so failure, so them failing is a 0.1, okay, and the failure of each of any switch is independent of the other switch. Okay, they are not reliant on it. What is the probability that the machine will break down? Okay, the probability that the machine will break down is 1 minus the probability that it does not break down, right? And it's not going to break down as long as none of them fail. Okay, so since each of them are failing with a 0.1, that means they won't fail, so there is going to be a success with probability 0.9. So we have a 0.9 multiplied by 0.9 multiplied by 0.9. So we get a 1 minus a 0.729, and therefore the answer is 0.271. Another thing that you could do is, again, that's going to take us a longer time, because if they're asking us what is the probability that the machine will break down, and a success is needed to control a machine. If the probability and the failure of any switch is independent, what is the, I think what it means is that if all 3 switches fail, no, success of 3 separate switches needed to control. Okay, that means that all 3 of them together need to be operational. Okay, so it will break down even if one switch breaks. Okay, so the probability of at least one switch failing. Remember, because it said that for the machine to work, all of them need to work properly. So even if one switch fails, then the whole machine will actually not be able to work. So what does this mean? Okay, so the first one fails, but the other 2 don't fail, right? Or the first one didn't fail, the second one did fail, and the third one did not fail. Or the first 2 didn't fail, but the last one failed. Or it could be, see, there's a lot of many possibilities. It could be that all 3 of them actually failed, or it could be that the first 2 failed and the last one didn't fail, right? Or it could be that the first one failed, the second one didn't fail, but the third one failed. Or it could be that the first one didn't fail, but the last 2 ones failed. So this is very lengthy. So it's always recommended to just use the fact that 1 minus the probability of the complement of this event is going to give you the same probability. So I've always used the fact that the probability of any event is equals to 1 minus the probability of the complement of that event. Okay, so this is enough for today. I'll make another video solving all the questions given after question number 9. So, inshallah, from question number 10, I hope this lesson was useful, and I will see you in the next one. Take care.